morning, everybody, and welcome to the ERC session on the next generation of artificial limbs that are shaping the future of medicine. My name is Telma Carvalho. I'm a scientific officer at European Research Council, and together with my colleague Nadia Almgiad, we will moderate the session where our grantees will present their results on this exciting topic. You will therefore hear on the last developments on prosthesis, and the main challenge is to make this fully embodied. This is to say that amputees can control them in an intuitive way and feel them as real parts of their body. So, missing a limb can lead to dramatic impairment in the capacity to move and interact with the environment, and to a substantial worsening of the quality of life. This deficiency is associated not only with the actual functional loss of a body part, but also with a large portion of the sensory motor cortex suddenly facing neural deafness, an effect that often leads to a painful phantom limb. Missing or damaged limbs can in principle be substituted by robotic limbs connected to humans with neural interfacing. Although a substantial development of robotic limbs was achieved in the past decade, currently artificial limbs have a complexity that is beyond the possibility of volitional control by the user as offered by the available man-machine interfaces. Current designs of advanced robotic limbs are not coordinated with the constraints imposed by neural interfacing or by human motor control and learning. The ERC, or the European Research Council, is a funding body of the European Commission with the mission of supporting frontier science, which is definitely what is necessary to tackle the challenges just described. Doing it requires the involvement of experts in different fields, namely in robotics, neuroscience, surgery, and man-machine interface, who shall work in a synergetic way to create a fully integrated symbiotic replacement of missing or damaged parts of the human body with artificial limbs that the user will feel and command as true parts of their body. This synergetic way of working is exactly what the synergy grants at the European Research Council are looking for. These grants, as all other types of grants that we offer, are bottom-up, being the only requirement excellence of the science and the researcher or the research team that is going to carry this research out. It is my pleasure to introduce three of the most distinguished experts in the field of robotics, man-machine interface, and surgery that have the ambition to realize this vision, allowing us to reply to the question, shall I walk, dance, or write again? With a definitely yes, you will. Those experts are pursuing a patient-centric approach that synergetically combines breakthroughs in surgery, neural interfacing, and robotics, as just mentioned. So let me start by introducing Professor Antonio Bicchi. He is known worldwide for his pioneering concepts in robotics, such as soft synergies for robotic hands. You will certainly hear more about this on his presentation. Professor Bicchi has several academic positions, being namely adjunct professor at the Arizona State University, professor at Pisa University, and senior scientist at Istituto Italiano di Tecnologia. Professor Bicchi shall work with Professor Farina, who is a pioneer in neural interfacing based on spinal motor neuron behavior. Professor Farina is internationally recognized for his work on biosignal processing and neural control of movement. Professor Farina holds several positions as full professor at several universities in Europe, like the University of Aalborg or Göttingen, but currently is the chair at the Department of Neurorehabilitation Engineering at the Imperial College London. They will be working with Professor Osman, who is the director of the Lab for Restoration of Extremity Function at the Medical University of Vienna. He is internationally recognized for innovation in surgical procedures of nerve and bionic reconstruction. Namely, he envisioned, developed, and successfully implemented the idea of bionic reconstruction, which is a synergetic neurotechnological approach in restoration of extremity function, which result in paradigm shift in clinical application of prosthetic technologies. Before giving the floor to Professor Vicky, I would like to remind you to post your questions in the chat, as this will be answered by the speakers at the end of their presentations. Now, without further ado, I give the floor to Professor Vicky, who together with Professor Farin and Professor Osman will let you know how they are realizing a new generation of prosthetics within their Synergy grant funded by the European Research Council.
Good morning. Thank you, Thelma, for the very nice introduction. You really made my life easier in introducing the project that we are talking about, which is Natural Bionics, the natural integration of bionic limbs via spinal interfacing. The talk is about prosthesis of feet and hands, mainly focused on hands, but also with interesting insight in feet. So wherever we look at human hands, we are amazed. We are awed by the incredible complexity, ability, and richness of our hands. We have 23 joints, 34 muscles, 3 nerves, 100,000, 150,000 nerve fibers. The hand is soft, is adaptable, also strong and resilient, and overall, it's very simple to control. So this is amazing, and if you compare with what you can have today with prostheses, then this is really humbling. Today's best prostheses have only up to 5 joints. They typically have no or very few sensors, and they rigidly interact with the environment. The human foot is no less important to humans. It is no less distinguishing from primates, for instance. The difference between the human foot and the primate foot is even larger than between the hands. It has 33 joints, 34 muscles, 2 nerves, which brings 120,000 nerve fibers. It is also soft, adapting to the interaction with the environment, and also simple to control. We never think of our hands, of our feet, while we walk or manipulate. So again, in the feet domain, the current foot prostheses show no joints at all, or very few, no sensors. They're basically made of one piece of flexible material. So our goal is to change this situation and make prostheses that are much more natural. So I will leave the floor to Oscar now, or Professor Assmann from Vienna.
Yeah, hello. To put these things into a more socioeconomic perspective, I will give you some epidemiological data in regards to limb loss. So we're talking about major amputations worldwide. A major amputation is either a below knee amputation or above knee amputation for the lower extremity, and for the upper extremity, it would be an above wrist amputation, meaning any hello, anything above the wrist then is a major amputation of the upper extremity. Now, in the United States, with a population of around 3.3 million inhabitants, we have about 85,000 amputations per year. And in Europe, it's about 300,000 per year, just because we have a larger patient group here. Now, about 1/3 of these amputations, because this pertains both for the upper and lower extremity, is regarded to the upper extremity alone, so which is in Europe about 100,000 amputations per year. Next slide. Now, if we look at this, we realize, and this is only data for the upper extremity that you're seeing here, that 61% are fitted with a prosthesis, and 25% have had a prosthesis, however, they don't use it or have difficulty wearing it. And 14% have never had a prosthesis. This is either because they live in a country where this is not provided because it's extensive equipment, or patients have had an amputation that is so difficult, for example, missing the entire arm, where these prostheses are just not provided. Next slide. Now, here are the main causes for dissatisfaction. So these are the people who have had a prosthesis, but however don't use it. And the main reason here is non-intuitive control, which means that the patient has a prosthesis, however, he cannot intuitively govern it. Lack of sufficient feedback is very important, and we will also tackle this in our research program here, meaning that we do not feel the prosthetic replacement that is being provided to us. And finally, it is insufficient functionality, which means that the robotics that are being provided, the hands that we have, are just not good enough and do not reflect the reality that we are in need of. Next slide, please. Now, to your left, you see a short video of a state-of-the-art prosthesis that is being provided today. And as good as it is, and you must realize that this patient has loss of the entire arm, down from the shoulder to his hand, and we see there's good bimanual dexterity of pronation, supination, open and closing of the hand. We also realize that this is a very clumsy procedure that we see. It's clumsy because it has a limited number of independent control sites. It has no natural sensory feedback, which means that you can see that even now the patient needs to look at the hand to have some type of proprioceptive feedback. There is no cortical representation in the arm, meaning no nerve or no muscle implants. That means that the information transfer is very limited. And finally, the interaction of the prosthesis with the object at hand, which here is just a small bottle of milk, is very difficult for him to realize. Next slide. So this is why we have come together as 3 different groups with the aim of having natural bionics as a research program that aims at creating a fully integrated symbiotic replacement of missing or damaged parts of the human body with artificial limbs that the user will feel and command as a true part of his or her own body. So the next speaker will be Dario Farina, and he will talk about how this is going to be interfaced. Please, Dario.
Yep, so we will achieve this goal by creating a bidirectional transfer of information with the human spinal cord. We will extract neural signals from the spinal cord through what we will call, as we will discuss later, a biohub, the human stump. And we will decode the information coming out of the ventral horn of the spinal cord in order to command robotic parts that are substantially different with respect to the current state of the art. And specifically, they mimic more the biological characteristics that Professor Bicky has explained at the beginning. At the same time, we will have to collect information from these innovative bionic limbs and transfer it back through the same biohub, through the spinal cord up to the brain of the patient, so passing through the dorsal root of the spinal cord and reaching the brain of the patients to achieve a sensation. In order to do that, next, we will have, as it has been mentioned in the introduction, to combine 3 fundamental disciplines that have been rarely combined in this type of research, at least within the same large project. And these are surgery, robotics, and neural interfacing. Next. In order to do so, we have put together teams from the Medical University of Vienna, led by Professor Assmann, and from the Italian Institute of Technology, led by Professor Bicky, and at Imperial College, led by myself, that together will work very closely with an approach that is patient-centric. So we will put the patient needs at the center of our research to combine these disciplines and to reach something that has never been reached before. We will then progress in the remainder of this presentation by telling you some of the achievements so far reached in the three main pillars of this project, starting with Professor Asman telling us about the surgical interventions. Oscar, please. Next. You're muted. You're muted, Oscar.
So hello again, I am Professor Assmann from Medical University of Vienna. I am a nerve surgeon. So my part in this project has been rerouting nerves, so the creation of a biohub. This is very exciting because it will provide the patient a sensory motor representation of the missing limb. And I will tell you what that means. Next slide. Before we go into the details, this is how we can reconstruct hands in the 21st century. To your very left, you see the very first hand transplantee patient in Europe. And this is a bilateral hand transplantee that has received his hand in 2001. And then we see various different parts of patient who have received a bionic reconstruction to have their hand function restored. Next slide. So I think the only indication today for a hand transplantation is the loss of two hands in a transradial level. Why? Because these patients have a dramatic loss of sensation and functionality, and this cannot so far be restored with mechatronic means. So I think until today, a bilateral loss of hand can best be reconstructed or restored with a hand transplantation. However, in a unilateral hand loss, like for example in the patient to your right, this is, I think, best restored today with bionic reconstruction. Next slide. Now, if you look at these are options to reconstruct hand function in a transradial hand loss. So to the left, you have a Krukenberg procedure. This is a very simple claw hand where the patient can pick up things and have very minimal dexterity. In the middle, we have a classic mechatronic or prosthetic reconstruction. On the right, we have a hand transplantation. Now, as I said before, I think a unilateral transradial amputation is not an indication for a hand transplantation because of the immunological burden to the patient. Next slide. And here we see a bilateral hand transplantee. Next slide, we see a video of this patient. This has been taken about 2 years ago. And this is the oldest hand transplantee worldwide with his hand still on. We need to remember that the cohort worldwide is about 130 patients that have had their hand transplanted, and about 30% of these had to be re-amputated. So that there's a large loss of hands that we have been put a lot of effort into, and chronic rejection will lead to hand loss eventually. However, as you can see, this patient has excellent dexterity. Next slide. Excellent two-point discrimination. And we can see even small things and small objects he can pick up with ease, and there's great coordination of the fingers. Next video. We see a bionic hand patient. We see again, there's excellent dexterity, great compliancy of the hand with the objects, and also great speed, as we can tell. Next slide. Now, I've talked to you about nerve transfers. Now, before we started to get into this project, we have tried to get an idea as to what actually we're working with. And we found out that there is about 350,000 axons leaving the spinal cord going into the arm. This is an immense amount of nerves that go and provide both sensation and motor function to the hand. However, to our surprise, only 10% of this nervous system are efferent and 90% are afferent, which means that movement, in fact, is a sensory phenomenon. Now, if you read in the second paragraph, there's only 7,000 spinal motor neurons responsible to move the hand and forearm, which to my surprise is a very small number that provides all the difficult movements that we do with our fingers and hands. So theoretically, we can display every single neural signal from the spinal cord when we reroute nerves into a different muscle. And now we get into the details of creating the biohub. The biohub means, no, keep it back, please. To the lower right, you can see that there is spinal motor neurons responsible for hand function in the lower spinal motor neuron column, which is only about 2,000 nerve fibers. And these are being rerouted into muscles in the region of the stump where the patient has lost the arm. And the amazing thing happens is that these neural information that is responsible for hand movement is then displayed in the muscle in the region of the stump. Next slide. Very recently, we have published this paper where we have done in an animal model a transfer of the ulnar nerve into the biceps muscle of a rat. The biceps being a very stupid muscle and the ulnar nerve being transferred into that muscle, which reflects hand movement. And to our amazement, not only that did the neurophysiology change, but also the architecture of the muscle changed, so that this muscle will then display the neural information responsible for hand function. Next slide. Now, in order to get the proprioceptive feedback back, it is important to also provide a sensory feedback back to the brain. Now, I've mentioned before that movement, in fact, is a sensory phenomenon, and this may be surprising to you, but if you think of your facial musculature has no proprioceptive capacities as itself. There is no receptors in the human facial musculature that can talk back to your brain. However, the skin overlying the muscles of your face can provide this information. And if you've been to the dentist, you will have realized that if your skin overlying your face goes numb, you lose the ability to have a detailed control of your facial musculature. Now, we have taken this phenomenon a step further to create the manunculus. And I'll tell you what that is. Next slide. So what we do is we have a muscle, we transfer the nerves, as I have told you before, the ulnar nerve, for example, that is responsible for finger movement, into a stupid muscle in the region of the stump. And at the same time, we will transplant a piece of dermal skin onto that muscle, which will then have the capacity to feedback detailed proprioceptive feedback back to the brain biologically. Now, Dario Farina will tell you more about the details as to how we listen into the language of the nerve as it's being displayed in that muscle. And then this entire construct is placed within the stump of the muscle, which we will then call a manunculus. Next slide. The word manunculus is taken from the word homunculus, which we will all know, which is a proportional representation of various body parts in the brain and cortex. And this will allow to create a neural map of the entire body in the brain. Now, in regards to the manunculus, next slide, this allows us to create a representation, a sensory motor representation of the hand in the region of the stump. Next slide. So here we see again the hand in the arm. So it is a sensory motor representation of the lost hand in a biological way that we can then decipher and create neural signals that then control the prosthetic hand. I think now it's time for Dario to take over.
Yeah, so the surgical interventions that Professor Assmann has described will allow us to create bioscreens, as he has mentioned, meaning muscular tissue that reflect neural information coming from nerves that have been surgically transferred. And now the role of neural interfacing is to interface and to interact with that with those electrical signals and decode the neural information that is traveling along the peripheral nerves in and out the spinal cord. The main challenge, obviously, is to maximize the we want to transfer as much information out and in the spinal cord, potentially all the relevant information for sensing and controlling a limb. Next. The neural cells that we are interested in decoding to decode the commands given to the prosthesis are spinal motor neurons that Professor Asman has mentioned. The spinal motor neurons are connected to muscles through peripheral nerves, and the surgical interventions that Professor Asman has described will allow us to move peripheral nerves into virtually any muscle that can be used as a bioscreen for these cells. Next. Now, the idea is to interface the muscle tissue, which is reinnervated, with a very high density of microelectrodes implanted, and this will complete the biohub. So the surgery will complete the nerve transfer, creating a bioscreen. The neural interfacing will provide the electrodes and the decoding techniques to read that information and to decode it in order then to transfer that information to the robotic parts that will be completely innovative with respect to the past, as Professor Bicky will describe. So what we have to do is basically to understand the neural code of movement once the nerves carrying this code have been moved around the stump appropriately by the surgical interventions. The challenge is that we need to intercept the activity of a relatively large number of cells, although, as Oscar Asman has described, these numbers are in the range of thousands. So from the engineering point of view, it is feasible to interface them. Next. So as we said multiple times now, the idea then next in terms of decoding the commands is to decipher the activity coming out of the ventral horn of the spinal cord with this combination of neural recordings and surgery. Next. Now, the challenge is, as I mentioned, the information transfer rate. So the challenge is really to increase the amount of information that we can extract. And in this, we would like to really make a breakthrough with respect to any other attempt of the past. Next. So in the past, the classic approach has been to use muscle electrical signals without the surgical intervention we described, but also without any particular decoding. So using a muscle recording rather than a neural recording. And the idea has been to detect electrical signals from the stump muscles, and then with various machine learning approaches to transform it into control of prosthesis. This has led to relevant results, next, such as the videos I'm showing you now. So this is known technology. This is work that Professor Asman, Antonio Bicchi, and myself have done together in the past before this project, allowing a quite precise control with classic muscle electrical activity processing, NEST. And this is a similar video from another patient showing what we can do as state of the art. This is probably the best we can do up to now before this project by using, as you can see, electrical activity from the stump. Next. So now, although this is impressive, this is very far from a real limb replacement. For the replacement of a really very large number of degrees of freedom in the range of, for example, 20 plus degrees of freedom in the end, as Professor Bicchi mentioned at the beginning, and a very large number in the leg as well. Next. So our breakthrough idea is to now put neural decoding into the game. So rather than considering muscle signals as they are, as in classic prosthetic control, we would like to go back mathematically, developing mathematical techniques that reverse engineer the generation of those muscle signals and go back to the original spiking activity of the cells in the spinal cord that has generated that muscle activity. So this is a breakthrough concept because it transforms the control of prosthesis based on muscle electrical activity, which is classic myocontrol, into a neural interface, meaning an interface with neural structures and basically with individual neural cells. Next. Now, this is again going back to what Oscar Asman has described. We did some homework before the project, and we asked ourselves, as Oscar has described, how many are these neural cells? And as said, these are not in a number that is unfeasible to interface. For example, the end, as it has been said, is controlled by approximately 2,000 neural cells in the spinal cord. From the engineering point of view, we can interface them. This is not a huge number. We can realistically interface every single of those neural cells. And if we can do that, then we can exactly replicate the neural code responsible for the movement of a missing limb. Next. Now, in an animal model similar to the one described by Professor Asman before, this is for the neural interfacing part, and this is already joint work in this synergy project, which is extremely exciting. In this animal, we have already the proof of concept of a nerve transfer, in this case, in what Oscar defined as a stupid muscle, which is the biceps of a rat. And now more, you can see here in the central picture, microstructures that are microelectrodes that interface that muscle. And those microelectrodes, which are in this case, approximately 50 electrodes, and then we will scale to hundreds or thousands of these electrodes over the following years, provides a reading of that bioscreen. So the muscle has been reinnervated by nerves. It behaves as a bioscreen, and then we put these electrodes that behave as pixels that can read the bioscreen. And then we can watch that bioscreen, and we can go back with mathematical techniques back to the spinal cord, which is what you see representatively in the bottom part of the slide. And we have already a proof of concept that is indeed possible. So we can go from the bioscreen to individual spiking activity of single cells in the spinal cord. So now this is extremely exciting because for the first time, we have a communication with the spine that goes at the level of single neural cells. Next. So this that I've just described. So you can see the electrical activity on the right from muscles. That's classic muscle recordings. And then now we have two breakthrough approaches. One is that muscle is acting as a bioscreen on a multitude of nerves that we will converge surgically and that represent the entire movement of the limb. And second, we read from this bioscreen and we go back to the spinal cord, effectively reading the neural code that is responsible for the control of a missing limb. In principle, we will be able to code the complete neural code for the missing limb. If we can do that, we can then control the advanced robotics that Professor Bicky is developing in an ideal way. Next. Now I'd like to underline that this neural interfacing concept is not only limited to prosthetics. So this presentation is on prosthetics, but I put this slide on, which I think is relevant to indicate that this is a breakthrough interfacing with the spinal cord with a variety of other applications. So within the project, we are also working on broadening the applications within this concept of neural interfacing with the spinal cord. Specifically, already within this year of the project, we have developed the first demonstration that we can interface with the spinal cord in spinal cord injury patients. You can see a picture on the left. This is work done in collaboration with the University of Pittsburgh in patients that have a brain implant, but that now we can read without a brain implant with the techniques that I've just described. In the middle, you can see a completely different application. Within this year, we were the first to look at the single motor neurons in the spinal cord in infants that are just a few weeks from birth. And so we looked at the way in which these infants are controlling their muscles in a way that was impossible before. And on the right, you can see another representative application of a study we are running with the University of Newcastle, Professor Stewart, on a monkey model of motor neuron disease, where the motor neurons in the monkey are interfaced with the same techniques I've explained to you. So this is just to say that we are using these techniques as breakthrough techniques in prosthetics, and then within the framework of this project, we are very excited that we can prove the validity of this interface in a very large variety of applications. Next. As a final discussion on the interfacing part, again, as Professor Asman discussed, we have a very innovative concept for providing sensory feedback. The innovative concept is to use biological receptors that we will transplant on top of the muscle bioscreen. And by using these biological receptors, we believe we can input information in the spinal cord and eventually in the brain of patients in a more natural way. So the interfacing part that we will work on will have the challenge of stimulating the biological receptor that we will transplant surgically. And stimulating the biological receptors has to be done again in an intimate relation with the robotic developments that Professor Bicky will describe, because the sensory information that we will translate in the BioHub has to come from the sensory information collected by the interaction of the robotic limb with the environment. And so again, you see an example of is this project in a true sense. So this was a very brief overview of the neural interfacing challenges. And now we will go through the third pillar of this project, which are the robotic developments. So I will give the word to Antonio Bicchi. Antonio, please.
Thank you, Dario. Yes, so the goal, the purpose of this part is to design the limbs that will replace the lost motor and sensory function. So our role is really this of closing this loop. It is the prosthesis, the bionic substitute of the hand or foot that has to actuate the motion that comes from the commands from the spine, and also to generate the feedback that will go through the manuncles back to the spine. It is not enough that we generate this motion and this sensory feedback. It is also crucial to the naturalness of our work that these sensory outputs and the generated feedbacks are consistent. They match the expectation that we have. So every time we send to our hand or our foot a motor action, we also generate an expected result from sensor, and we match and we compare what we really get from our sensory system with what we have learned in our youth. So it is important, it is crucial that our limbs, bionic limbs, have the same, generate the same matching interaction and matching the natural anticipation of the sensory consequences of motor command. These are generated through interaction with the external world, and it is important to know that this interaction is mechanical at the end of the day, and our part in the interaction is a hand or a foot that is soft. So that explains why, if we want to embody the necessary intelligence in this prosthesis, we have to use soft bionic limbs. Coming back to the complexity of extremity control, we have already made the point that natural bionic replacement needs human-like dimensionality. You can see on the left here that human hands are using all of their 20+ articulations to do even a simple task such as uncapping a jar, while existing prostheses are much limited in that regard. But the upper limb has 30 or more degrees of freedom, and the lower limb 25 or more. There are also the capability in our body to change the stiffness, the impedance, so that adds for more complexity. How do we achieve this in the design of a realistic, reliable, rugged, practical prosthesis? And also, how do we make it possible for a person wearing that prosthesis to manage that complexity without thinking of it? So to help us in this endeavor, we have two assets, two enablers. One is from science and one is from the technology. In terms of the scientific enabler, we have this beautiful theory of sensory motor neural synergies that has helped us to understand how the motor control of the hand is not flat, but it is organized in hierarchical synergies that are primitives of motions which organize the complexity, so that to us, the motion of the hand is much simpler in our views. So these are patterns of motion that really organize as an orchestra the many degrees of freedom of the hand. And if you look at this into some detail, you also realize that not only they come out of a beautifully simple mathematical description of the hand movement, but they also have or correlates in the cortical representation of hand motion, as shown in this previous paper of ours. In this project, we will find the correspondences to this organization in synergies in the spinal signals that are accessed to the Braille hub, so that we will be able to control through the same mechanism. If we now think of these primitives, how they generate motions of the hand, you should think of these primitives not as the actual motions of the hand, but rather as references for the hand, our inner representations of the hand that drive the hand motion, like the wireframe in this animation, are references for the rendered hand that is attracted to this wireframe, but interact with the outside environment, with the object, to determine the final position of the hand, which therefore can be different depending on the different interaction. If you look at this video here, you see that the human hand does a very similar thing. Here we are asking a subject to grasp an object that is not really there. So it's just a hologram. You see what the person does. The person really goes much beyond the target, goes inside. So the inner representation of motion in this person is such that it would not fit the exact shape, but it is attracted by that image, and it will generate, because of this intersection, the necessary forces and necessary shape adaptation. So there is an intrinsic intelligence embodied in the very way the synergies are built in the mechanism. So in the previous work before this project, we had implemented this idea of soft synergies for robotic hands that could exploit some of this idea to simplify motions and, for instance, use this compliance with a simple hand to take a book out of a shelf, which is, if you spell it out in terms of programming, a daunting project, but can be done very easy by our own hands. And now we are turning this into prosthetics. So the idea of having a soft hand enables you many different things. So you can see on the top right, for instance, that you can be both delicate and adaptive to the shape, using all the 19 degrees of freedom of this hand with a very simple control that at that point was only made of muscular EMGs that we got from the stump. So this was before using the more advanced neural interfaces that Professor Farina has described. Also, the naturalness of this hand, of this early prototype, is apparent from the adaptability and robustness in other videos. So these soft synergies provide a natural physical connection to the biohub with the external world. But that is not enough. We also have to address sensory feedback. And the number of peripheral receptors in the skin, muscles, and tendons is itself daunting. We use nearly instantaneous dimensionality reduction of elementary sensory inputs through invariants that are called also sensor synergies and priors. That's the only way we can deal with the many thousands of input that come from every receptor in our skin and every receptor in our tendons and muscles. Otherwise, we would be at a loss if we had to think of that. So they are organized in mechanisms that compress this information, and as in any compression mechanism, there is room for illusion, for some mechanism to get through the cracks. And this is shown, for instance, by perceptual illusions. Perceptual illusions are very well known for vision. For instance, in this animation, you see the famous barber pole, which is always only turning, but you seem to see it moving upwards. And that is one of the effects of these invariants and priors that we stick on our perception. Very similar things happen in the tactile domain, although these are not as widely known. And for instance, if you have an object that moves under your finger, your estimate of the direction of motion of the finger is biased by the texture of the object itself. So by using this perceptual illusion, we can understand the mechanism better, and then use those backdoors to simplify stimulus delivery, because those are the things that really count to our perception, not the many detailed information that should come from every single receptor in the skin, but rather their abstractions that are those that are known to our central nervous systems. Also, another thing that we will exploit in this project is our knowledge of the fact that receptors are not uniformly described. So if you want to know, for instance, how your hand moves, your main source of information are receptors in the skin, not just in the joints, but from the skin deformation, we recover how the hand is moving. This has been mentioned briefly by Professor Asman before, talking about the hand, the face muscle system, but also for the hand it holds. Now, it is interesting to know that the distribution of receptors in the hand is not uniform, and it has a pattern. And this pattern is depending on which are the most important and most frequent motions of the hand. And it is strongly correlated with that. So by understanding this pattern of motion, understanding how we can distribute our sensor, we can reduce the number of sensors and make it more effective and matching our expectations. So when we are going to build a sensory feedback, as mentioned before, we have several options. First of all, we have to build tactile sensors of the prosthesis, and we are doing that by putting gloves on the skeleton that I showed before, and that are implementing both the pads, the compliance that we need in our pads, and the sensors that we need to convey back the information. And then we will address the sensing rather than through some of the methods that have been discussed before in the literature, as was discussed by Professor Fanir before, by acting directly on the biohab, on the skin that has been grafted and reinnervated on the biohab, through mechanisms that are placed directly in the stump, as in this prototype that we have recently completed in our project, where you have here the displays that go into what will be the biohab. Another topic of this project is locomotion and soft feet. So in locomotion, for both prosthesis and also for robots, typically feet are rigid. You see on the left here a carbon fiber foot. Everything is fine when you walk on a flat terrain, but when you have an obstacle on the terrain, then you realize how bumpy the walking can be. If you have instead an articulated foot that resembles the natural foot, then you see that adaptation allows you a much smoother trip over the obstacle. And these results already show that with comparison with a rigid foot in the middle, a soft foot, articulated foot on the right, provide a much more aligned contact force with the knee, similar to what you have in the leftmost panel from a human with his normal sound foot. One important thing in our project is to make hands and foot that are natural. And in the naturalness of our prosthesis, it is important that you also consider not just performance in manipulation or locomotion, but also the perception that you have and the feelings that the patient has. It is a very important role of our hands, for instance, is social interaction and also self-interaction. When you hold a hand or when you touch your own face, you have something that is very important to make you familiar with your own hand. When you do this with artificial hands, unfortunately, with rigid hands, the interaction is all but natural. As you can see here, and indeed, if you look around at videos of prosthesis, people that have rigid prostheses almost never use them to touch their own body or even to interact with others. How can we do this better? Our soft hand allows more natural integration with the body. And you see here the prototype that we realized recently of the previously shown hand in a new version that is now more versatile and richer, and that also has a more anthropomorphic skin-like cover. You see the hand now that interacts with a person, and let me show some results of the use of this hand. So this is the Cybathlon, which to those of you who are interested in prosthetics is a well-known competition that is organized by ETH in Zurich, and that is to sport for people with disabilities. What Formula One is to the sports. So in this is to Paralympics. In Paralympics, athletes compete with equal prostheses. In Cybathlon, athletes compete with different, very high technological prostheses. It is very interesting that Cybathlon is run every 4 years in correspondence with the Olympics. And here is the pilot of our team who ran the series in 2019 in preparation for the Cybathlon 2020 that will be run in a few months this year. So here you see Maria, who is a pilot, it's also a collaborator in our group, that uses the hand and exploits the softness to increase the embodied intelligence and the dexterity of this hand. I will not go into the details of this task. Let me just briefly mention that the outcomes of this series, we didn't win. A professional team of Osur had the first and third place. Our team placed second and fourth. We were happy with that. Of course, it's not important to win this time. It will be important when the finals will be there. But it's also to be noticed that the MDS Soft Hand Pro was the only research hand in this competition. More important than these, I think, are some results that we gathered after the race. So there are a few candid pics that I would like to show with you that were taken with the subjects unaware of the taking pictures. So this is Maria making a phone call and using the hand to use the phone, or Maria opening a bottle of Coke. If you look at the zoom, or if you zoom up this picture, you see that the soft hand that we designed according to the principles of the natural bionic is shaping around the object much more like the human hand than a rigid hand would do. So there is this degree of embodied intelligence in the control of the hand that will help us realize natural interfaces. And if you think of self-interaction, you can see here that Rosa and Maria, our pilots, are using the hand in a very natural way. And they're not thinking of the hand they cross the fingers, for instance. Here is Maria is focusing on the task before starting, and you can see how she stretches the knuckles before starting. Maria is also using the hand for just making gestures. And in social interaction, here you have Maria that dances with an engineer. These things you don't do if you have a rigid hand. And although he is an engineer, she's pretty good at teaching. And here is Rosa doing massage with the hand. Again, think of the difference with rigid devices that typically we have now available. This is after hours, Maria doing something that you'd never think of doing with a rigid prosthesis. I would leave to Dario to conclude the presentation.
Yes, very briefly, because we... And we have also shown how intimately related all these areas are, which is really the characteristic and the main feature of this project. Where do we want to be in 5 years? This will be, actually, this is the question also that the ERC posed us, and we posed ourselves this question in the first place. Well, we would like to have a clinical platform that would allow the highest level of bionic reconstruction in lower and upper limb amputations. And in parallel, as you have seen, this goes with a huge amount of basic scientific research, which is extremely important. It goes from human biomechanics and robotics to human neurosciences. And so in all these areas, we are building a scientific platform with new discoveries that are related to basic science. So with these core platforms from the clinical view and from the scientific view, we hope within 5 years to build and to further establish a center for bionic reconstruction, physically located in Vienna, which is the center where our patients are monitored and treated, and to make this center as a center of reference globally for innovation in prosthetics and bionics. And with this, on behalf of Oscar and Antonio, I would like to thank you very much for the attention, and we will be, of course, very happy to discuss with you and answer your questions. Thank you.
Thank you all. That was a very interesting presentation. And the floor is now open to questions. Thank you all again for this wonderful presentation and this little glimpse into our future. Maybe I will open the discussion with a simple question. So, I mean, it's very exciting and you want to dream of extra things that you could do with this kind of hands, and how complicated it is for the human brain to handle this extra thing you can do? I mean, I know that for the moment you just hope that you can reflect on the normal hands, but how well the human brain is able to handle these capacities, and how flexible it is?
Maybe I can take that question. So we do nerve transfer surgery since about 20 years. Nerve transfer surgery means that we take nerves from one part of the body and transfer it into another part of the body. And the human brain is amazingly quick to relearn new strategy. So, for example, I remember I had one patient who has had a brain stroke and he could not move his face and he kept biting his lip because he couldn't feel his lip. And he just noticed when he was bleeding that he bit his lip. And we did a nerve transfer from a nerve to the shoulder to reroute it into the lip nerve. And it took him about 6 weeks. Whenever he bit his lip, he felt a pinch in his shoulder because he then realized that he's fighting something. Makes sense what I'm saying?
Yeah.
So it took him about 6 weeks when he realized when he's hurting here, then he's biting his lip. So the brain is amazingly powerful to adapt to new neurological situations. Now, a more recent story is, for example, a patient who has driven into a tree and he could not flex his elbow. And we rerouted a nerve that is responsible for making a fist into his bicep. And it takes patients for a number of weeks to realize that there is a different neurological reality. And yes, as I said in my talk, movement is a sensory phenomenon. This is one of the big aha moments of my own life to realize that, because we all focus on nerves that drive a motor. Now, I have 3 children, and one of them plays a violin. And I asked my daughter, and I say, how do you remember all the finger movements when you play the notes? And she said, Papa, I don't remember, but my fingers know. They know exactly where to go. So I think this is an important observation, that movement is indeed a sensory phenomenon. And what that means is that when we do nerve transfer surgery, or now nerve surgery for prosthetic replacement, is that we need to provide patients the feedback. And that means that, for example, if we do a nerve transfer surgery, I have the patient sit in front of a computer screen and I show him the movement that he's actually thinking of. So that means we didn't have time to show these videos, but we have patients that do not have an arm, but we have done the nerve transfer surgery, we have created the biohub, and then we sit the patient in front of a computer screen and he envisions hand function. And then he sees on a computer screen moving his fingers and hands, and that's how he's learning. So I think that is one of the big steps, I think, forward, is that we need to provide patients a feedback and then a training process with which they can learn these new movements.
And it doesn't depend for how long the patient has been amputated?
Yeah, this is a very good question in regards to time. And yes, it's true, the earlier we rehabilitate patients, the easier it is for them. Also, youth is better than old people. Now, I'm 55 years old. It's going to be really difficult for me to learn new things. But yes, movement is something that can be learned even in old age, but it's better for the younger patient. Now, we have patients that have lost the arm several years back, but still they can learn how to address this prosthesis if they have learned with the visual feedback to address that.
Okay then. So really interesting, all those stories you tell us. This is really interesting. So we were interested to know how long can this biohub be used, because this is going to be interfaced with other materials, which are, of course, materials that are accepted by the body, or in principle, they are certified to be accepted by the body. But in fact, it's still an external material in your body. How long can this biohub be used?
So I'll take quickly that question and then I'll give over to Dario. So the biohub per se is a biological construct. So that once the nerves have grown into the muscle, I think this is a permanent situation. We know this from patients many years back, that this is a situation the patient can live with. Now, what you're addressing is to have the implants, meaning the grids that will be implanted. And for that, I'll give the word to Dario.
Yes, so that's a very good question, Thelma, and the answer to this question is also the basis of the rationale for which we use muscles to amplify nerve activity, because one solution that would come in mind immediately is to interface nerves directly. So one would ask, why do we need to move these nerves around and transfer them into muscles if we can directly interface nerves? So this is indeed done, but nerve interfacing is very complex for what you are mentioning, meaning that nerves are small structures. They're very delicate because they are narrow structures, and the system that we put in the nerves have a good likelihood to damage the nerve and to not function properly after a certain period of time. Muscles are very good structures to interface. And that's why we support our concept in which we surgically put the nerves into muscle, and then the muscle is used as a biological amplifier. So we engineers look at the surgery that Oscar is doing literally as putting an amplifier into a wire for which we want to amplify the signal. And that amplifier is a bulky one where we can put electrodes for a very long time. So before the project, Oscar had run a clinical study on muscle implants with another technology, but conceptually is the same, where patients have structures, electrodes implanted in muscle for several years. And it doesn't provide any issue to the muscle, any problem to the neural structures, and it's very stable over time. So we believe that with this concept, we can have also the implants, in addition to the permanent nerve transfer, staying permanently, actually. There is no reason for which they should have a limited duration.
Okay. Sorry.
I may add that normally if you have any foreign body implanted into the human body, there will be a soft tissue connective sleeve going around it, which is a type of scar, if you will, collagenous fibers that will form around it. And this will be stable for a long time. And we know this from impedance measurements, that this will change within the first 4-6 weeks after implantation. But once it has stabilized, this will be stable for a long period of time.
Okay, then. Before we go to the questions we now start receiving, I just have one last question also related with that. How is embodiment changing in time? Is it related to the acceptance of the implant by the amputee, or is there other mechanisms that are involved to increase this embodiment sensation?
Maybe I'll take that for the beginning. Embodiment, I think, is one of the large plans that we have for any type of prosthetic replacement, because it means that the patient actually accepts the prosthetic part that has been given to him. And I think a very large part of embodiment is sensation. It means that the patient actually feels what he's governing. So it's intuitive control for one part. It means to be a very fluent way of controlling the device, but also it means that the patient actually has some feedback from the device back to his body. There is numerous experiments in the last years that sensory perception is the biggest part in regaining embodiment to prosthetic replacement. But maybe Dario or Antonio want to share something as well.
Well, maybe Antonio underlined a few times also the role of the proper representation of the limb and softness. So I will leave this.
Yeah, this is something I tend to stress. There is a big part of embodiment is the matching of the motor action with the expected perception that you get out of an action. And that I mentioned already, and this is one of the goals that we have in making this interaction natural, which at the end of the day also is something that happens mechanically, physically at the interface between the prosthesis and the environment and the external world. So you have this part of the loop that we designed in the animations before. That part that has also to be natural, as well as the part that concern the human body directly. And second thing is a very important part of embodiment and satisfaction to the patient is related to these social and own body interactions that are really core, we believe, to this. If you can touch your own body or you can interact with people in a natural way, that will give you the ownership of the prosthesis that you have, and that is another direction of large investment for us.
Okay. Nadia, will you go further asking the first question we received in the chat?
Yes, so we received, I mean, it's a bit related to what we just touched upon already. One question was about how does the efficiency of the receptors change over time? But I think we covered partly this question. Then someone was asking about whether you would be able to provide any kind of limb, for example, for patients who don't want to have limbs that look too real and want them in different colors. But maybe we can keep these questions for the end. And
I think that is a very good question indeed. If you want to take that right
do you
away,
want to take it now?
if you, I mean, it's up to you.
Do you think if because we're saying that if the limb looked more like a human limb, it's easier to accept it, but is it always the case, or?
No, that is a very good point. Indeed, it's not to be taken for granted that a prosthesis should look like the human part that it is replacing. I would rather focus the attention on these matching of perception and action. That is important, but the look is not necessarily that important. Indeed, there are plenty of subjects that do prefer to have a not they have a prosthesis that does not look like, that does not pretend to be natural. And there is a whole lot of work that is going on. In our group, we have a person that is Maria, the person that you've seen in some videos, that is a designer and a social designer in some sense. That she's studying exactly how people perceive the prosthesis design, how they want to have it, how that fulfills their expectations. And it is absolutely true that, for instance, that many children don't want to hide the prosthesis. They are, very happy with their body, nonetheless, and they are even proud of the prosthesis if it looks technological, if it looks advanced. So that is something that we have not to conceal. So our goal is not to make something that is not seen as a prosthesis. Our goal is to do something that is not felt as a prosthesis by the user, but can be looked at as a prosthesis, as a nice thing to wear, as a nice thing to use, as a technological aid to our own lives, like we use glasses without having any embarrassment.
Someone
I can add one 30 seconds. The question is also interesting looked on the other way around. If we look at the far future, we could also assist and then enhance humans. So they augment the human capacities. So we are talking about patients now, but the gray line between patients and able-bodied individuals may disappear once we assist systems that work better than our biological systems. So this is very far in the future, but since this is a discussion where the audience may be diversified, it's also interesting to know that there are groups who are working on hands with 6 fingers and trying to understand if the human brain can control this kind of hands.
this is actually just a comment on what Darius said on the future, but this also poses other ethical concerns, no? Because this was also something that how you actually control. You will, of course, in your prosthesis, you will have some safety boundaries that will not make the prosthesis dangerous. How do you actually ensure that this remains so in the future, and an individual that has such a prosthesis cannot actually manipulate it and make?
We've lost you.
I think what Thelma wants to ask is basically how to avoid the prosthesis becoming a weapon if it gets developed maybe too far, and what kind of barrier there is in the field to avoid this kind of thing happening.
Yeah, so I may answer this in part. So we have constant discussions with prosthetic producers. So these are the large companies who are eventually producing the prosthesis. And this is an ongoing discussion that has much to do with regulatory affairs. Mm-hmm. Now, obviously, if we talk about the upper extremity, it is not so critical because if the hand fails, then maybe the cup drops. But if the foot fails, then you may have a severe injury because you fall down the stairs and you have a very may break your. So it may be really dangerous. So we've had these discussions going on with another project. It's called Posterior Integration, meaning that there is prostheses that are being actually attached to the skeleton of the human body. And the problem we face is that these extra skeletal parts are then interfacing with prostheses, and the prosthetic providers do not provide the link. And so we've had that happen before, that patients then actually have the prosthesis fails and they have a fall and they break their hip. And so this is a regulatory affair problem. So one of the rules is that obviously the patients must not fiddle around with their prosthesis. If it breaks, they need to send it back to the manufacturer to have it repaired.
So you cannot pimp it up, basically.
Yes, yeah, no, so exactly. So, and also there is fail-safe mechanisms that need to be very carefully assessed before any new prosthesis or any new prosthetic part comes to the market, so that patients will not be harmed by whatever is being produced. So that is, I think, a very important thing. Now, the other spectrum is that we have, what Dari has been discussing before, is that some patients want to look like a bionic man. And I think this is a philosophical problem in the end. I don't know if you know about transhumanism. It's a philosophical tendency that tries to overcome human limitations with mechatronic means, if you will. Now, I personally believe that the human hand as it is wonderful, and any mechatronic counterpart will always be a very poor depiction of it. But yes, I agree that in some ways and forms, a mechatronic part can supersede human abilities. And we need to be very careful from an ethical point of view to find the balance as to which patient will profit from a mechatronic replacement and which not patient or maybe subject may not profit from it, and we must stay away from that. Now, I'm a doctor. I'm not an engineer, and my maybe I come from a different perspective, and I see patients that have a deficit whose lives I want to improve, and I realize, yes, there is some tendencies in that trade where we encounter maybe subjects or patients that just want to improve. But I think this is not, at least not from my perspective, the goal that we're pursuing.
Thank you.
I may add, I agree. Of course, there are other applications. It is conceivable that we use these hands and even these interfaces with our own neural system to control a hand that is a third hand. It's not just a replacement for your missing hand, but it's used as a third hand. And that will give you this augmentation that Professor Farina and also Professor Asman were alluding to. And that I think is a good thing to do in some cases. Could be helping you in your work, or could be, and we are initially looking into that, could be useful for a person who has lost the complete control of his hands because of stroke, for instance, and can be helped by a third hand that he has under control. So those things are good, other uses. Of course, dual use of technology is something that is always worrying us, but it's also hard to control. We will not be able to do anything if a patient of ours would use our prosthesis to use a gun, for instance. And I do. I have met a patient who wanted to try with a gun because he's simply passionate about guns, and nothing we can do about that. So misuse of prosthetics is not easy to prevent, probably, but it's not our job either.
Of course, otherwise you don't do anything, I guess.
Yeah.
Thank you. Maybe we can take the more technical question, no? The last one, Thelma?
There is still one more question in the chat. Yeah, sorry, I was cut out, so I didn't, I don't know what was already asked or was not asked. But still, I don't know if there was this question asked if the artificial hand will have sensors that will somehow protect the integrity of the hand. For example, if the person touch something that is very hot, if this is considered in the sensors that hand has or not. That was something that one of
the
audience was asking if the hand will consider this or not.
It is an important concern. Thermal and pain sensors are important, and we will definitely incorporate them in the eventual version of our hands.
One thing I may add, the pain sensation actually is an interesting type of sensation. Of course, the immediate thought would be that we would never provide pain to amputees. But on the other hand, pain is a protective sensation that is important in many respects. So there is only one group who has developed a neural interface in this case and sensors in the prosthetic that provide painful sensation through high-level electrical stimulation in order to inform the patient with a realistic painful sensation of danger to the prosthesis. But this, of course, is not only for danger in the prosthesis, because this could be done in other ways, but is also related to our initial discussion on embodiment, because pain is a very important sensory feedback for embodiment. If I feel pain, I feel a part definitely as part of my body. So this again is very much in the future, but considering all the sensations, even those that now would look ridiculous to add or not appropriate to add, considering the state of the technology, may in the future be something that is more and more relevant.
I may add something to that discussion. One must not forget that perception and sensation must be immediate. When one thinks if a fly lands on my finger, it takes about 30 milliseconds to reach my brain. Now, I think, Dario, you can correct me, but I think the most sophisticated systems that are around, it takes them about 150 to 300 milliseconds. So in the end, this is old information that reaches us. However, the way we work as a human body is an immediate sensation that pertains both to pain, but also in regards to just regular sensation. And I could give you many stories for that. We don't have the time for that. But I think whenever we think of embodiment or feedback, one thing that must be minded or must be thought of is also the immediacy. That is why we have proposed to have a neurobiological system that is right in the biohub, meaning that we close the loop primarily with the sensors of the dermal strip on the muscle, which will provide feedback from the proprioceptive receptors in the skin that is overlying the muscle, meaning that is very quick information that closes the loop.
May I ask a follow-up question? I was wondering with your biohub. So basically, when your fingers touch something, do your brain have the impression that it's your finger with a prosthesis touching, or do you feel in the thumb?
Yeah. So there is two different things that we talk about. So it's external sensation, meaning that the sensory capacity of the finger. Which I think the most important in a prosthetic replacement is first touch. Mm-hmm. So meaning when you have a hand and a prosthetic hand and you touch an object, you need to know, when did I touch the object? And that obviously needs to be related to the physical mechatronic hand that you are engaging in. So there are concepts even now in place where we have sensors in the finger, meaning just the index finger and the thumb, where we can have feedback from the mechatronic finger back to the brain. So the way we interface this is either by direct nerve stimulation. That is something that we have published in the New England Journal of Medicine just a few months ago. So that is possible even today. The problem is that the way we feedback directly to the nerve is with an electrical stimulation that the patient may feel as an electric stimulus, but not as touch. And I think that is an important point to bring up. We may be able to say topographically it's the index finger or it is the thumb, but it's not the sensation of touch. Sensation of touch is difficult because we have about several thousand mechanoreceptors in the fingertip, but these are spatially and temporally related to each other. And the way we feel an object, whether it's rough or smooth or edgy or whatever it is a concept. It is not. It is just different mechanoreceptors being stimulated in time and space. Mm-hmm. And I think that is just very difficult to reconstruct in a mechatronic way.
Thank you.
So still going on this part of touch, and because I think it's a very interesting part, which is crucial for ensuring embodiment. So you talk about a mesh of that is going to be placed, and this is going to contain some magnetic particles that are going to be activated. How is the activation made? Is it externally? Because you also mentioned that the prosthesis is fixed to the bone, so I believe that this is all done from internally to the prosthesis. How is this stimulation made?
Yeah, so I don't know, Dari, you want to take that, or should I continue?
Yeah, maybe yes. One important thing, it's also related to this question and to the previous question of Nadia, is the key aspect to reproduce a proper sensation of touch, which indeed is difficult to reproduce electrically, is that the skin transplant will be reinnervated with the nerves that were going to the missing fingers. Mm-hmm. So transfer game is done both in terms of decoding the commands, but also for the sensor information. So we are rerouting the information. So yes, if the idea is that if you touch yourself the stump in the biohub, where that dermis structure has been transplanted, the nerves that were delivering information to the brain from the fingers, to make the example of the fingers, will be activated. And so effectively our idea, but this is a big risky scientific hypothesis, probably the biggest risk in the project, is that you will exactly feel the missing finger. And that's what makes the difference with respect to any other approach so far. Then the point is, how do you stimulate indeed that transplanted skin? Because you cannot do it with your finger. And tell me, the magnetic particles is one approach, but there could be a number of other approaches. So the key point is not how we do that, but the key point is to prove scientifically that we can reproduce the sensation of the hand in that little piece of transplanted skin where all the sensory nerve of the missing end have been rerouted.
I may add to that. I know we have only 25 seconds left, if I see correctly, but it's a matrix that we are transplanting, meaning there's many different sensory receptors that are being present in that piece of skin. Now, if you, for example, bend your finger 90 degrees, you're stretching the skin overlying the joint and you're compressing the skin on the other end. And so that means you're relaying both proprioceptive stimuli and sensory perceptive stimuli at the same time. Now, we have no idea how the patient will be able to differentiate as to what's what, but I think time will tell when we have the first patients with whether this will work or not. But as already Dario said, it's an exciting project that we'll be working on.
Thank you. Thank you. So thanks very much for the presentation and for answering the questions. I think we are over time.
Thank you so much for everybody that was attending and for asking questions. I think this was very exciting and we could stay here another 1 hour and a half listening to all those stories. Thank you so much for doing it. Thank you.
Thank you also, and bye-bye.
Thank you.
Yes.
Thank you very much.
Bye.
Bye-bye.